So it's my pleasure here. I'm home from National Central University, Taiwan. And I'm from civil engineering, so a little different from management. I'm similar as Professor King and Professor Lai, but from different aspects, not focused on the monitoring or the transportation. I'm focused on how to do the simulation, especially for the geotechnical engineering, and this is the NCU campus. So it is very welcome to Taiwan. So this is the content, introduction, and some federal cases, especially focused on the landslide, and then how to do the physical modeling and why we have to do the physical modeling, and finally we have to briefly summarize this. So this is Taiwan. We just located at the boundary of two plates. That's the reason why you can see that number. There is a small island. It's Taiwan, and we have a small. This number is 71, means that we grow up 71 millimeter every year. So it will grow up every year. Then it did too. We have a lot of peaks, more than 3,000 meters. So do you know how many peaks higher than 3,000 meters in Japan? Do you know? Check it. It's less than 30. But in Taiwan, we have more than 250. Yeah, so within this small island, so that's the reason why we have a lot of geotechnical problems. And then also, because we just located at this boundary, so we have 33 faults, including one normal fault and 33 reverse faults. And then, just like a sweet potato for Taiwan, and then but 90% of population just focus on the 1/3 of the land. That's the reason why. So just like I mentioned that within this 2/3 of the land, almost no people. So you can see that this is we have a lot of beautiful place. This is a Penghu, and it also formed by the volcano. So within this small island, we need to do some study about, especially not only focus on the seismic behavior caused by the earthquake, but we also have a lot of natural disasters. So this picture shows that, yeah, we prove that most of the population located at 1/3 of Taiwan. This is the ninth picture. So we need to pay more to recover, because this is the data from the past maybe 50 years. So you can see that the disaster occurred, we need to pay more. And then we have more and more hurricanes. We have more and more typhoons. And this is a dissipation of the energy of each disaster. It increases with the time. And then from the past study, we know that the hurricane or typhoon would trigger the landslides. And then within the top 10 cities of the vulnerable city around the world, there are 2 in Japan, there are 2 in Taiwan. So we face a lot of disasters, include the earthquake, flooding, and wind problem, and so on. So since this is the environment of Taiwan, and almost, I believe it is the same as in Japan. So we have a lot of fatal cases, especially focused on the landslide. So we have different catalog to different type for toppling. So we can see that this, what it is, this is not, please do not focus on this rock. We focus on this. This is a kind of toppling. And this is a landslide in Afghan, and we can find a lot of features of sliding. And then this is the case filed maybe 7 or 8 years ago in Taiwan. So this landslide just cut the highway. And okay, as you can see that sometimes we will think that, okay, landslide maybe triggered by the heavy rainfall, but as you can see that a lot of landslide or debris, it is shining day. So, and then this is a case in Hiroshima, and this is a case in Shaolin Village, just like Professor Lai said, that this Morak typhoon attacked Taiwan. So this is a before and after. So the whole village disappeared. And then the landslide may be caused by the different reason. This is maybe caused by the river system, or caused by the gravity, or caused by the heavy rainfall. And this is what's caused by the Gigi earthquake. And this year is GG earthquake is 1999, so already 20 years ago. So this is before and after GG earthquake. So you can see that it would triggered by a lot of landslide. And then this is a mechanism of the landslide triggered by the earthquake. So what do you think about what kind of slope is dangerous or what kind, or safe? Only slope is steep or gentle slope. Which one is safe? Actually, it cannot just focus on the geometry, but we still need to focus on what kind of material, right? So, and this is evidence why we have this kind of tree. That's because when they are young, they are pushed down, but they are not died, still grows out. So this is evidence in the past, yes, landslide occurred. And from the Google Earth, you can find this kind of picture. So we also can find a lot of evidence there in the past landslide occurred. So go back home, check the Google Earth around your home, okay? So this is also we can find in the mountain area, the road, we have a lot of cracks in the gap between the foundation and the house. So this is, so what we can see from this, actually we can see a lot of a release joint. So there's only one way at the east of Taiwan, but it always the rockfall. So it always blocked by the rockfall. And that's the reason why we have to build a new road. So just like the students say that the target of the engineer is to prevention, mitigation, and recovery. So we need to find some way. So for the engineer, yes, we have a lot of structures. For example, the external stability, based on the external stability or based on the internal stability, we can strengthen increase the effective safety of the structures of the slope. And then we have different ways. For example, the gravity walls, we need to put some drainage system. We have a tie back or soil nails walls. So we have used the wired reinforced metals, something. And then we have a soldier pile wall, we have a sheet pile walls to increase the effective safety of the structures. And then we have a MSC wall system, the same. So this is a countermeasure. This is why we have to do something. And then now we already have some countermeasures. And then in the past, for the engineer, we need to design, right? We need to know how about the factor of safety now. So this is a theoretical, how to get the factor of safety. And then that is 2D, and this is 3D, and this is a numerical simulation. But I would like to ask one question. How do you know the result is correct? Right? So you need to verify it. That's the reason why we need to do some tests or need some data from the observation. So how to do the study of geotechnical problem or how to design the soil structure interaction, that is, we need the full-scale monitoring result to feedback to the numerical simulation. Or if we do not have this kind of data, we need to physical modeling to check the input data. That's a reason why we need to do some tests. Always in the lab, we did some tests, right? So if we would like to simulate real prototypes site behavior, for example, I would like to simulate 100 meter steps that I would like to build a tunnel there. How to simulate in the lab? Usually we use a tank 1 meter and we use a small tube to simulate. Okay, I tell you that this small tube is 6 meters tunnel's behavior. Do you believe that? Maybe have some relationship, but we still use a scaled model, but put in high G condition. So for this, small models can subject to the same stress and strain level. So that's the reason why we need to have this kind of environment for the model. But how to create this kind of artificial gravity? Actually, I believe for civil engineering student, everyone knows that for the first one is the Atterberg test. It kind of use the impact load to create this kind of field. And second is the centrifugal force, and then third is centrifugal force. So here, I would like to introduce about the centrifuge modeling, and it have its own scaling factors. So this is NCU centrifuge. We use this to simulate a lot of geotechnical problems. And then, of course, they have some scaling laws, and then they have something arrows about the boundary, about the particle effect. But now I just talk about what we already done. So this is the advantage we can create the same stress and strain relationship as compared to the prototype. So this is NCU National Central University. This is our lab. And then we have a lot of facilities. We have an actuator, we have 1G shaking table, we have wind tunnel, and reaction frames and channels for the hydraulic test. And then this is a NCU centrifuge. So we can, the radius 3 meter and capacity 100 G tons. It means that 1 ton's motor can span into, we can fly in 100 G. G is the Earth's gravity. And we have a 1G shaker. So during spanning, we can input the base shaking to simulate dynamic problems, especially simulate the soil liquefaction problem. So we have different container to simulate different faults. So for example, this is to simulate the reverse fault. And then we have a lot of different devices to apply the load and then to scan to get the surface change. And then we can, for different material, for clay material, we consolidate it to make the soil sample. And to sandy material, we use a polyviation to create this model. And then we have a lot of different sensors to measure what we are interested in. And then, so when we start the test, it starts to span. So as you can see that the platform is here, we put the model here, so it will shift up. So this is the camera installed at arm. So it seems a little delayed, okay. Okay, in the past, we did a lot of tests. For example, the tunneling problem in clay material, in sandy material, and then within this few years, we focus on the soil structure interaction and liquefaction, or the high-level wet canister behavior and the slope stability. So this is a landslide retaining wall system and with a PIV system. So as you can see, it close to critical state, it moved, so we can use this kind of video to do the PIV and know where is the gap. And then this is a dynamic behavior of embankment, and this is a dynamic behavior of the pile foundation. So we have different structure, upper structure. So during test, we input the dynamic load so we can get the moment distribution, and then with different, this is L pile, middle, the moderate pile, and the small pile. So we can get different behavior at 0.5 hertz input motion, and this is 1.0 hertz input motion, and this is 1.5 hertz. So we can see that is because the different pile will have its different predominant frequency of different response. So we input the different base shaking that will lead to different response of the pile. And then this is for simulate for the normal pile foundation. So the same, so during flight, we can apply the load to know the PY curve of the monopile foundation for the wind turbines foundation. And then this is especially in Taiwan, because we would like to develop the wind turbine energy. And then, but around Taiwan, we have the soil is a liquefiable soil. So this test is that we input the base shaking, and we would like to know how about the PY relationship during soil liquefaction. So we, okay, already liquefied, and then now we push. So, and then we would like to, we also can simulate the storage facilities on the liquefiable soil layers. And then we have a LIP project. So this year, we just have a meeting here, right? So quickly goes. So this is, we would like to, we can use this kind of device to study about liquefaction, and then the lateral spreading, and then the deformation of the ground surface. And then this is used to, also it can be used to how to reduce the settlement, or how to reduce the lateral spreading. So we can put some sand piles, or we can put some belt. So during it liquefied, you can see that all the excess water pressure move upward to the ground surface. And then if we have a building here, and then we put some sand pile around, does it affect to reduce the settlement or differential settlement, or it can reduce the liquefaction time? Yes, this is what we did in the past. And then this is a dynamic problem, dynamic behavior between the buffer material and the canister. So during spanning, we input the base shaking, and then the last part is source stability. So this kind of tool, not only for the research, but also the education. So you can see that this is a bearing capacity problem. This is active. This is passive earth pressure. So this is in the book we know that sometimes the professor just tell you that, okay, planar failure surface would occur, and sometimes they tell you circular failure surface would occur and pass through the toe. Sometimes not pass through the toe. Why? When? How? So through this test, we can show that why planar failure surface would occur and why the circular failures and pass through the toe. So this is not only for the research, but also for the education. So that sometimes we see that this is a retaining wall system to see how about its behavior under different conditions. And this is a failure of the sandy backfill, so retaining system. And then we can know the failure mechanism. This is the advantage of this kind of technique. And then this is Mingan's research about the landslide. So if you have question, ask him. Yeah, so in the past we can know that maybe some thin layers would affect the failure behavior, but from the theoretical analysis we cannot separate this. So that's the reason why we did this kind of research, and then we got the result. And after the test, we can check how about the water content distribution, how about the shear strength distribution of the model, and then we can summarize that. How about if there is a thin layers horizontally or dip direction or reverse dip direction, that will affect the distribution of water content. Of course, it will change the distribution of the strength. And then of course, that will affect the failure surface of the slope. So not only this, but this is, we input the base checking, we apply the rainfall, so that will lead to different failure behavior. And then, of course, they will, because of different infiltration of the material, we can get different failure condition. So you can, as you can see, that it is the advantage of centrifugal modeling is we can just show you what would happen in the future. Okay, so this is this is a front view of the slope. So when we, it collapsed. And then after collapse, if the typhoon comes, so it will have some rainfall, and then you will see some erosion and take the soil to the downslope. And then we would like to find some countermeasure. So this is without grass, and this is with grass. So after shaking or after rainfall, that will lead to different failure condition, and they can, of course, can show the effect of the vegetation on the slope surface. And then this is base shaking. We input the base shaking, and this with grass and without grass, of course, we can get a different result, and to see what efficiency of the vegetation. And then, of course, we can put some small pile, concrete pile, into the slope, and then that will lead to different failure behavior. For example, this is 2 by 2, 3 by 3. This is no pile. This is 2 by 2, 3 by 3, and this is 4 by 4. So this we can see that it's a kind of brittle behavior, but this is a kind of a softer material behavior. And then the same, we can do some to verify the numerical parameters of the sheet pile wall system, and then we can know the distribution of bending moment, the settlement of these structures. So finally, I would like to say that actually it is very interesting. It is very useful tool, or for students, maybe it is a very big toy. So if you're interested, welcome to come to NCU, do a test. Thank you very much.